Good morning, everyone. So it's my very great pleasure to introduce Kartik Nayak from the University of Maryland. At the moment, he's a fifth-year PhD student under Prof. Katz and Prof. Xu. And he's been a recipient of a Google Fellowship in Security. And he'll be talking to us today about Oblivious Computation.
All right. Good morning, everyone. I'm very excited to be here. Today, I'll be talking about how to use Oblivious Computation to compute on private data and to obfuscate programs. And towards the end, I'll talk a little bit more about my research in general and some of my ongoing and future work. So let us say we have this scenario where we have two or more hospitals, and together they're trying to compute information of the type, is some treatment better than some other treatment? And they want to do this based on the joint information of all the hospital's patient data put together. But laws such as HIPAA do not allow one hospital to share its data with another hospital. So you have this scenario where you have your input data, which is patient data that is private, and yet you're trying to perform some computation on top of this, and the computation itself may be public. You have a complementary scenario where you have companies such as 23andMe, which have patented genomic algorithms, and they want to send their programs to the end user in such a way that the end user can find its own ancestry information. In this scenario, 23andMe wants end users to use their program, yet not learn what the program is doing because the program forms the trade secret for such companies. So you have a dual scenario here where your program is private, but the user inputs themselves may or may not be public. So my research has focused on designing and building systems for such privacy-preserving computation. And as I just mentioned, broadly it falls into two categories. One, how to secretly outsource data and enable computation on it. And second, how to obfuscate programs. And today I'm going to discuss this with a lens of access pattern obliviousness, which in a nutshell is the art of hiding memory access patterns. In this talk today, I'm going to first discuss access pattern obliviousness, and this is going to be a short introduction to what it is. And then I'll move on to contributions on computation on private data, and finally obfuscation of programs. And towards the end, I'll talk a little bit more about my other research on blockchains and some of my ongoing and future work. So whenever some computation is being performed, you have a CPU and memory where your memory will store your data and your program. And whenever an instruction is being executed on the address and data bus, you will have the corresponding memory location that is being accessed and the data word. If I were to enable computation on private data, the first step would be to keep this data private. And one way to achieve this is to leverage a secure processor, which ensures that all the data in your memory is encrypted, and the data on the data bus is also encrypted. But what you still do reveal is which memory location you're accessing. Such secure processors exist in the form of Intel SGX, but the question is, you're still revealing these addresses and whether it is okay to do that. If we look at this specific example, which says, if some secret variable is true, then I'm going to access memory location X, otherwise I'm going to access memory location Y. And just based on which memory location is being accessed, now you would know exactly what the secret variable is. And this tells you that, well, access patterns can indeed reveal some secret information. And if this seems like a toy example, there exist more relevant attacks. Actually, this attack is right from the MSR lab, where some computation was being performed on JPEG images. And this was done using Intel SGX. And in the process, just by looking at page level access patterns, one could recover the image to the right from the image to the left. And this tells you access patterns can indeed leak a lot of information about your data. And although these attacks are relatively recent, the problem of protecting access patterns was discussed around 3 decades ago when Goldreich and Ostrowski came up with the notion of an Oblivious RAM, which is a cryptographic primitive to provably hide access patterns to data. In this talk today, it is not necessary for you to understand an Oblivious RAM scheme as such, but just to give you some intuition, here is what all Oblivious RAM schemes do. Let us say I want to access memory location 5, then an ORAM scheme would access memory location 5, but in addition, it would make a few more obfuscating accesses, say to memory location 7 and 2. And once I perform this access, what most ORAM schemes do is they shuffle data around. The reason why you shuffle this data is because if you do not shuffle it, and if you want to access 5 again, then you may reveal some sort of frequency or co-location information. But if you shuffle data around, perhaps if you're still accessing 5 again, you would be able to hide which memory location you're accessing. And because you're making these obfuscating accesses and shuffling data, you actually end up touching more memory locations than you need. And one key metric that you're trying to reduce in an Oblivious RAM scheme is bandwidth blowup, or the number of memory locations that is being accessed. And typical Oblivious RAM schemes have a polylogarithmic bandwidth blowup. So given this background, one key challenge in this space is to make access pattern obliviousness efficient. And this we need to do given that we know that there is a lower bound which says if I have n passive memory locations, by passive I mean you can only read and write to this memory, then you need to incur at least a logarithmic overhead for every access. And the base of the logarithm over here is the number of registers stored in the CPU. So given this lower bound, one thing that you can do is you can design a scheme that actually meets this lower bound with as good constants as possible, or try to circumvent this lower bound altogether by changing the assumptions involved in the lower bound. Second, whenever I have to move to performing a large amount of computation, I would want to parallelize my computation. And turns out parallelism with obliviousness comes up with its own set of challenges. For example, now the communication pattern in between the processors should not reveal any more information. And this constraint is in addition to the standard constraints of parallel programming, where you would want to have a low processing time and low communication between processors. And finally, I would argue whenever you want to design a system, you would want to design it with some practical constraints in mind. For example, if I'm trying to use a secure processor, I should know exactly what properties such a secure processor provides. And that is useful both for security and efficiency. For instance, one question that you may ask is, can the trusted processor store state in between invocations? Let us try to ask this question to Intel SGX. So whenever Intel SGX is executing some instruction, it has context of the previous instruction it has executed. So in that sense, you can think of such a processor as being stateful. But more recently, we have seen attacks called as rollback attacks, where you could switch off an Intel SGX machine and then provide it with an old state and then roll back execution. So in that sense, you can think of Intel SGX as being a stateless processor. And in the second part of my talk, I'm going to discuss how such assumptions in conjunction with obliviousness can actually matter in security of schemes. But more generally, I would say that if privacy-preserving computation were to be a success, it is essential for the fields of cryptography, architecture, systems, and programming languages to work in conjunction. With that, let me move on to discussing my contributions towards computation on private data. And specifically, I'm going to talk about a secure graph parallel framework called GraphSC. And in this framework, I'm going to show how it is usable. That is, you can design programs with programming abstractions that you already know, in such a way that this framework converts it into an efficient parallel execution, and you achieve some notion of security that I'm going to discuss. And you're going to see results which say what took 1.4 hours previously can be performed now 20x faster. And specifically, let us take this as a running example where, let's say you have Netflix, and Netflix wants to compute user recommendations on this data set. So this data set has, in the first column, you can see users. In the second column, you can see movies. And in the third column, you can see what rating each user has given to the movie. And given this, Netflix wants to compute user recommendations, that is, for a given user, which movie the user may want to see next. And even if we don't need security over here, one thing that Netflix would want to do is, given such data sets tend to be large, you may want to exploit parallelism. And just for expressiveness, you may want to use frameworks such as GraphLab. And GraphLab is just one such framework in a class of frameworks, which is targeted for a class of algorithms called graph parallel algorithms, or vertex-centric programs. The reason why they are called vertex-centric programs is because at any point in time, you're always thinking like a vertex. So a vertex in the graph, based on its own data and data of its neighbors, is trying to perform some computation. For example, you can think of page rank, where the page rank of a web page depends on its own page rank, and the page ranks of other web pages that are pointing to it. In fact, the example that I was describing earlier on computing user recommendations can be expressed as a bipartite graph between users at one side and movies at the other, and the edges represent the rating that a user has given to a movie. And turns out the result that I'm going to discuss over here in general applies to all map reduce operations as well. So one of the reasons why these graph parallel frameworks are nice is because you just need to remember 3 simple abstractions, and they are called scatter, gather, and apply. And I'm going to explain them in turn. And remember that at each point in time, you need to think of the computation as being from a vertex's point of view. What would a vertex do next? The first abstraction is a scatter abstraction, where every vertex sends some data to its neighboring edges, and the neighboring edges update their own data. The second abstraction is complementary, where a vertex aggregates data from all of its neighboring edges, and the vertex may update its own data. So the example over here shows a gather by vertex B. And finally, an apply operation. In an apply operation, every vertex and every edge applies some function to its own data. So the example over here shows an apply by all of the vertices. And turns out just having these 3 abstractions is very powerful for a large class of algorithms. And the reason why these graph parallel frameworks are nice is because you have usability. You just need to express functions using these 3 abstractions. And then these graph parallel frameworks give you efficiency and parallelism, that is, you can easily use the compute clusters that you already have. Given this, the goal of GraphSC was to have a secure graph parallel framework, that is to have security in addition to all of these 3 goals. And GraphSC gives you exactly that. So let us see what I mean by security in this context. So let us say we have a secure processor, and it has your graph stored encrypted, and it is trying to perform some computation, let's say computing user recommendations. What I want in the end is to ensure that this computation does not, it hides the data on vertices and edges. And second, it hides the structure of the graph. That is, the fact that there is an edge in between 2 vertices should not be revealed. And although I'm explaining all of this assuming a secure processor over here, later on I'm going to relax that by abstracting this secure processor using 2 different parties and running a secure computation protocol on it. But for now, let us assume that we have access to a secure processor.
So how is the data encrypted? So how is this data gathered in the first place and encrypted?
So in this particular example, you can assume that a user just submits an encrypted data, and it just communicates with the secure processor. In the secure computation scenario, it's going to be slightly different, where a user secret shares its data to non-colluding cloud service providers. So this is the scenario if we have access to a single processor. When we move to multiple processors, then we have an additional challenge in terms of how to split this computation into multiple processors. And we still need to ensure the same properties. That is, we want to hide data on vertices and edges and hide the graph structure. And turns out how you parallelize it may have an effect on how we achieve these properties. So given this, let us try to see how we can achieve this in our scenario. A first strawman would be just to use an Oblivious RAM. And an Oblivious RAM ensures that all access patterns are oblivious. And it is usable because I can use this with any program that I like. But the problem is that Oblivious RAM constructions tend to be sequential. That is, you cannot easily parallelize it. And a much more subtle constraint that comes into picture is that once your data is in an ORAM, all subsequent accesses will incur a polylogarithmic overhead. So given parallelism was something that Oblivious RAM did not achieve, let us try to achieve parallelism and try to do something where for every vertex, I have a secure processor trying to perform the computation on that vertex. Such a solution will give you parallelism easily. It gives you usability because you're still in the GraphLab world. And it also gives you efficiency. But the problem is that this does not give you security. And this is because the communication in between one processor and another processor will reveal information of the existence of an edge. One way to fix this is to ensure that there is an all-to-all communication in between these processors. And there you would achieve security, but now this would be at a cost of v-squared communication. One thing that prior work has done, and this was for this specific example, they came up with a handcrafted computation that achieved some notion of efficiency, and it was secure. But the problem with such approaches is that this was very specific to one algorithm, and for every algorithm you'd have to think ground up on how to make it parallel and oblivious. And they only achieved some partial notion of parallelism in this case. So given this, let us see what our work does, and this I'm going to explain with the key idea involved in an oblivious gather. And this I'm going to first explain assuming a single processor, and then I'll move on to how to parallelize this. And for this example, let us still assume that we have this bipartite graph, or let me slightly simplify this graph so that I can fit it on this slide. And you can still think of the vertices to the left as being users and the vertices on the right as being movies. And let us say we have a very simple computation that we are performing, and that is how many people watch a particular movie. So on this vertex x, in the end, you would want to see the data being stored over here. And because you're just performing a counting operation, the data on each of these edges is 1. The way I'm going to represent my graph is using a simple array, where each cell of the array represents either a vertex or an edge. For example, the first cell over here represents vertex C, the second cell represents edge AX, and so on and so forth. And in general, all vertices are represented by using a yellow background. The first step that I'm going to do in this process is to sort this data using an oblivious sort operation in such a way that a vertex is preceded by all of its incoming edges. So you're going to see vertex x being preceded by edges ax and bx. An oblivious sort operation, by definition, is data-oblivious, so it does not reveal any information about your data. And now, in a single sequential scan, I can perform my aggregation operation. So whenever I reach an edge, I'm going to collect data and aggregate it. And whenever I reach a vertex, I'm going to deposit that data there. So we collected 1 and 1 from AX and BX and deposited it at vertex X. And that is the simple aggregation operation. So over here, we are doing it for a simple counting operation, but in general, you can do this for any associative and commutative operation. The oblivious sort operation in principle takes E log V time for a graph of E edges and V vertices.
So in this computation, are you allowed to reveal the number of vertices and the number of vertices on either side of the partition?
No. So this computation by itself does not reveal that information. So in practice, what you would end up doing over here.
I'm not asking about I'm asking about your problem formulation. You want to hide that.
You want to hide that. So the computation by itself does not reveal it. But what may happen is that your input and output structure is such that the inputs and outputs itself reveal how many vertices are there.
Well, but in this case, I can learn the sum of vertices and edges based on your representation itself, right? The input there.
No. So all of this data is going to be encrypted, so that you will not know whether a vertex is a vertex or an edge. Whether each cell is a vertex or an edge.
I will know the sum of.
You would know the summation of
Right. But
you
I
would
would
know
not
the data
know
size.
like what's the size of each partition is, or how many edges.
Yes.
And
Yes.
you want to protect that even at the end of the code.
Yes, unless your input output, the initial input or the final output reveals that, because in many cases your final output may just say, give me values of all vertices. So your oblivious sort operation over here takes E log V time for a graph of E edges and V vertices. And in practice, you would actually end up using something like a bitonic sort, which incurs E log squared V time. And the sequential scan requires order E time, so this requires a total work of E log V. One key aspect about such an operation is that this can be easily parallelized when you have multiple processors. So let us see how we do that. Remember, at the end of an oblivious sort, we have a vertex preceded by all of its incoming edges. And in general, this problem looks like the following. You have an array of interspersed white and yellow cells.
I'm sorry, would you be able to go back to the earlier thing? So what is the output of this computation?
Right now, I think just for this operation, it is just aggregated and everything is stored encrypted.
Okay, so if I want to access the output, I should know the position of my
So once you're done with performing, so here's what a program is going to look like. It will be a sequence of scatter, gather, and apply operations in some particular order. Right. And in the end, if you want, for example, say data corresponding to all vertices, right. I just need to perform an oblivious sort again in such a way that the vertices are at one end, and then you can reveal just that data.
To reveal the output, so then it's okay, got it. Thanks.
Okay, so in general, your problem is going to look like the following, where you have an array of interspersed white and yellow cells. And for every yellow cell, you're going to aggregate the data in the preceding white cells. And the goal over here is to parallelize computation in such a way that each of the processors performs an equal amount of work. That is, you want to distribute the graph evenly so that the total amount of work is not too high. And in addition, you would want to achieve obliviousness. That is, the communication in between these processors does not reveal any information. And we do this by dividing the array equally in between different processors so that the number of vertices that one processor is responsible does not matter. It is a summation of vertices and edges that a processor is responsible for. And this is done in such a way that a processor is connected to logarithmically many other processors, and the amount of communication in between them is logarithmic. I'm not going to go into the details of exactly how this is achieved, but this is actually a generalization of the more well-known Sorry.
Can I ask a question on this? So, do you do the oblivious sort on the multiple processor or
yes.
single first?
Yes.
Or just split them?
We do it on multiple processors. We implement a bitonic sort. Okay. And because it is a network sorting algorithm, it's easy to do that. So it turns out that problem is actually a generalization of the more well-known parallel prefix sum problem, where let's say you have an input array, and at the output, for the ith element, you would want the summation of the first I elements. And let us say we have one processor working on each cell. And this can be done easily in a logarithmic number of steps, where in each step, each processor is performing some sort of a divide and conquer algorithm, and this is being done in sync with all other processors. With that, here is what the complexity of these operations look like. If you would have used an ORAM baseline, it would have required e polylog v time. Our solution for scatter and gather can perform it in order e log v time, and for apply, it can do it in order e time. And in parallel, as I just mentioned, the depth of a computation is order log v, and although I did not mention apply, the depth of that computation is constant. So until now, I have assumed that we have access to a secure processor, but turns out we abstract this secure processor using two non-colluding cloud service providers, and we use a secure computation protocol in between them. So let me take a small detour and explain what secure computation is, and then let us see how we can apply this in our setting. So secure computation protocol allows two parties or two or more parties, in this case two parties, let's say one with input x and the other with input y, to compute some function f of xy in such a way that one party does not reveal its input to the other party. And if I have access to such a protocol, let us see how we can use this in our setting. First, for my data set, I can encrypt this by just secret sharing this in between two non-colluding cloud service providers, let's say Netflix and Amazon. And secret sharing ensures that each share by itself does not reveal any information to either Netflix or Amazon, but together they have all the information that is necessary to perform the computation. And now they can just run a secure computation protocol with the algorithm that I just described earlier. And this ensures that Netflix never learns Amazon's share and vice versa, and that means they can learn the output without knowing the input ahead of time. And this ensures that your data on vertices and edges is hidden and the graph structure is also hidden. So for a specific implementation, we used Yau's garbled circuits, and we built this on top of FlexSC, which is Oblivion's backend, and Oblivion is a secure computation framework we were working on at the time. In case you haven't heard of Yau's garbled circuit, that is fine. It is just a secure computation protocol that we used. So given parallelism was one of our key improvements, the first thing we wanted to do was try to run this on as big a computation as we can. And we did this for the task of computing user recommendations, and the algorithm that we implemented was sparse matrix factorization using gradient descent. And we could do this on a movie lens data set of size 1 million, where when I say 1 million, I mean the number of vertices and number of edges in this graph together is 1 million. And the size of the computation was about 1 trillion garbled gates. And at the time, this was the largest ever computation that was performed using secure computation. And this we did using 128 CPU cores, which is what we had access to in our lab at the time. Comparing this to prior work, they could do this computation only on size 16,000 ratings. And for the same size data set using 32 CPU cores, what took them 1.4 hours took us less than 3.5 minutes. And this 20x improvement is primarily because of the way we efficiently parallelize it. But in addition to parallelism, we do this generically for any program that can be expressed in these graph parallel, in the graph parallel style. And for them, they just handcrafted this computation for this specific example.
Can I ask a question?
Sure.
If the number from 1 million become 10 million, how would the computation in terms of CPU, memory usage?
So in terms of time, it's
time,
yeah. In terms of time, it would be it behaves as n log squared n.
Okay.
So it would be almost linear, but there would be a log square component that would also come into picture.
And what about CPU usage and the memory usage?
So when we implemented this was CPU bound. Right now it is communication bound because with newer algorithms, newer processors have access to AES-NI, because of which these computations are now faster, and now it is communication bound. So in terms of computational resources, I'm saying it would take that much amount of time using the same amount of computational resources that we are using over here. If you can have higher amount of computational resources, which I'm going to get to next, then you can still have possibly the same amount of time, depending on how many resources you use. So let us see how.
Sorry, so I didn't follow the switch from like talking about ORAM and like parallel computation to like secure computation.
Okay.
So why was that necessary? So it might be a dumb question. So I just didn't follow that switch.
Okay. So the results that we have apply in both these settings. One, where you have a secure processor and you're trying to hide memory access patterns. And turns out in secure computation, the problem is slightly different, where you have a RAM program and eventually you want a circuit. And an important intermediary over here is the notion of an oblivious program. So the place where this ORAM or these oblivious algorithms come into picture is the design of these oblivious algorithms, which is the hard part. And once you have an oblivious algorithm, converting it into circuits is an easy translation. I'm not sure if I
just going to ask a sort of related question, but
Sure.
Just again with the relationship between ORAM and what you're talking about. So when you're talking about the Oblivious sort, for example, do you still need ORAM anymore, or are you like
No.
custom, or basically looking for a good Oblivious sort?
We are just trying to get rid of an ORAM over here. We are not using an ORAM altogether. Yeah.
You don't want ORAM.
Yeah.
But
So you could have made, so you're just trying to make it oblivious, and obliviousness and achieving obliviousness and writing a circuit, they're synonymous. So once you have obliviousness, converting it into a circuit is a one-to-one translation. I'm not sure if.
We'll look into it later.
Sure. Okay, so in terms of parallelism, so let us say, so this is the high-level result. On the y-axis, you see the execution time, and on the x-axis, you see the number of processors, and both of these axes are log-scaled. And the different lines over here correspond to different graph sizes. And as you can see, as we increase the number of processors, the computation time reduces. And although it is not clear because this is a log-log scale, it is actually true that as you increase the number of processors, the decrease in computation time is almost linear. And finally, just because we had a framework, we did this for a bunch of algorithms and not just for one specific example. And the same result holds for all of these examples. So with that, I discussed GraphSC, where you can take programs, return in these abstractions of scatter, gather, and apply, and you can convert them efficiently into, and GraphSC converts them efficiently into a parallel execution using secure computation. With that, let me move on to the second part of my talk on obfuscating programs. Turns out the problem of achieving obfuscation is relatively old, and there has been a lot of approaches to do this. There have been heuristic approaches to obfuscation. For example, this is one example, and I have a question for you. What does this program do? Or for that matter, what does this program look like? Any guesses? I think if you squint your eyes or if you go further behind, perhaps it would be easier. Sorry?
It's Flappy Bird, right?
Yes. So this is a Flappy Bird. So a game that was very famous, I think, a couple of years ago. Okay. And turns out if you execute this program, you can play Flappy Bird on your terminal. So such approaches to obfuscation tend to be efficient, but they actually give you no guarantees on what it obfuscates. And at the other end, it is known that it is impossible to achieve software-only program obfuscation in a strong sense. So given this, we are trying to come up with a scheme for obfuscation by using some other assumptions. There have been approaches in cryptography to achieve this. For example, they have introduced this notion of indistinguishability obfuscation, which is at this point inefficient and not strong enough in practice. They have introduced this notion of using secure hardware or trusted hardware tokens, but turns out most of these schemes use strong cryptographic primitives such as fully homomorphic encryption or non-interactive zero-knowledge proofs, or they just try to obfuscate Boolean programs instead of RAM programs. There have been approaches in the architecture community, but most of these approaches are used to hide inputs and assume public programs, and many of these architectural solutions actually reveal access patterns. Given that our goal was to, our goal in HOP, which stands for Hardware Makes Obfuscation Practical, was to achieve an efficient obfuscation scheme using a trusted processor, and we prototyped a hardware system to do the same. In this process, we introduced some optimizations which allowed us to perform up to 240x better than a baseline scheme, while still being up to 76x slower than an insecure system. Before I explain what our obfuscation scheme is, let me quickly define exactly what security properties we are looking for. And let us say in this ideal world where we have access to a trusted third party, we have Wei Dong who has a program he would like to obfuscate. He wants everyone to use it but not learn what this program is doing. And let us say Jonathan is trying to execute this program on his own inputs. So all Wei Dong will do is send his program to the trusted third party, and Jonathan will just send his input to the trusted third party, which will execute this and give a result back. And let's say in addition to the output, it also reveals size of the program and some execution time, which is fixed for all inputs of the same size. The reason why we're thinking of Jonathan as being the adversary over here is because he's the one who's trying to learn the program. And in the ideal world, he never has access to the program because it is the trusted third party who has access to the program. Jonathan only has an oracle access to the program. In the real world, and we want to ensure this for all inputs that Jonathan may have. In the real world, instead, you have this scenario where you have a secure processor which may have a small amount of trusted storage, and it stores everything outside in an encrypted form. And in this new world, what you can do is Wei Dong can send his program in an encrypted form to Jonathan, and Jonathan can just send the program and his input to the trusted processor, and which will perform an execution with the main memory and finally return the output. We're going to assume that the adversary has access to this entire memory all throughout, and in such a way that he can modify parts of memory if he likes, because we are envisioning this computation to be local. And what you want is the kind of obfuscation guarantee that you get to the left to be the same as the one on the right.
Who encrypts the input?
No one encrypts the input because it is the adversary who is trying to run this program. on his inputs.
So he's not, because I was confused by the lock on the input. So you're saying, oh, it's the problem. No, just.
All right, and turns out assumptions of the form whether such a trusted processor can store state in between invocations actually matters for security. So first we are going to assume that such a trusted processor can store state in between invocations. That is, we have a stateful processor. And let us try to construct an obfuscation scheme in this scenario. So whenever some execution is happening at every point in time, the processor is going to read an instruction. And this instruction can be a simple move instruction or an arithmetic instruction, or it can actually be a memory access. And whether or not it is a memory access is something that is available to the adversary. So the first thing you would want to do is you would want to hide whether it's a memory access or not. And one way to do this is to ensure that for every non-memory access, you actually perform a memory access as well. Second, based on what I have been saying earlier, we would want to protect our access patterns and use an Oblivious RAM over here. Third, because the adversary has access to the entire memory and he can modify parts of it, your trusted processor would want to authenticate memory at all points in time to ensure that the memory is not modified. And it would keep an authentication token within itself. And finally, you would want to run this program for a fixed time t for all inputs of same size, just so that the adversary does not learn how the program behaves for different inputs of the same size. And this is what I'm going to refer to as a baseline scheme later on in my evaluation. And turns out if you do this, you would achieve some notion of obfuscation if you're running a single application. If you're running multiple applications, let's say concurrently, in that case, the state corresponding to one program needs to move out of the token so that you can feed it with the state corresponding to the other program. And such context switching motivates the formulation of a stateless processor. Again, a stateless processor is something that does not maintain state between invocations. So at the end of the invocation, it would give out an encrypted state that it stores, and it would expect the adversary to send this state back at the next invocation. And if I have such a stateless processor, here is something that an adversary can do. He will execute the first 10 instructions, and now it is the turn of the adversary to execute the 11th instruction, say. But the adversary will send the state corresponding to the 10th instruction again and make the processor execute the 10th instruction again. And based on 2 executions of the 10th instruction, it will try to learn more information. And turns out such an attack, which we call a rewinding attack, in such an attack, in this scenario, an adversary can actually learn information. And the problem is that Oblivious RAMs are not secure against such rewinding adversaries. Because I have not explained an Oblivious RAM scheme as such in this talk, I will not go into the details of the exact attack involved over here. But what I will still give you is an intuitive but imprecise explanation of why that happens. Let us say my memory location of interest is memory location 5, and the 2 obfuscating accesses are to 7 and 2. If I rewind execution and if I run it again, I still need to access memory location 5 because that is needed for my correctness guarantees. But the 2 obfuscating accesses may be to 2 different locations. And if I keep rewinding and if I just perform a set intersection operation, then I would exactly know which memory location you're accessing. And although Oblivious RAMs are used to hide memory access patterns, we are not achieving that at all.
So remind me again, why do you want to consider a stateless process? Is it because you don't want to assume that the entire computation is done in one go, the adversary can like reboot the machine in between? And
Yes.
like, why is that a practical concern? Like, if the adversary reboots, just start from the beginning. And what kind of programs are you thinking? Like, are these long running programs?
So any program that may be long running, because so such computations tend to be much slower than existing computations. So if you want to context switch, one way to do this is to ensure that your processor is stateful and it remembers context of what's outside.
But all I need to remember is one counter, right? It's like I just need to write my state as a counter, and then I can keep track of progress.
Precisely. So if you can maintain that, and if you have a stateful processor, well and good, you can do that. But what we show is that even if you do not remember, or if your processor does not remember this information, you can still achieve the same guarantees.
So for this specific problem, can you fix it just by using PRG at the beginning?
That is possible.
Are there other attacks that this doesn't fix, or does that like fix everything?
This fixes it. Yeah. So specifically over here, we make sure that the adversary commits to his program and input ahead of time, and then you use your randomness based on a pseudo-random function that depends on the program and the input. And in this case, even if you rewind, you will still make sure that you use the same obfuscating accesses. So with that, I've explained some of the key elements involved in this construction. Let me move on to quickly describing the optimizations and quickly describing the architecture of the system. So we have two optimizations over here. The first optimization tries to reduce the number of memory locations that you're accessing. And this we need to do because ORAM accesses tend to be expensive compared to arithmetic instructions. And this, at a high level over here, we're just trying to interleave the number of arithmetic and memory accesses. And the second optimization over here tries to use a small amount of trusted storage within the secure processor. And if you have programs that exhibit locality, you would incur a scratchpad access instead of a main memory access. So here is what the architecture of the system looks like. We have a secure coprocessor, which works in conjunction with the host processor, which is the adversary. And your data is stored in an ORAM memory, which is encrypted. We started off with the RISC-V, started off with the Verilog code corresponding to a RISC-V processor, and we modified this to include a scratchpad load instruction, which was used to feed the data and instruction scratchpad. For an Oblivious RAM, we used a variant of path ORAM called recursive ORAM, and this is something that was built previously. And finally, we had encryption and decryption units to ensure that all the data outside is stored encrypted. And here is what the high-level result looks like. On the y-axis, you have slowdown to insecure execution. And on the x-axis, you have different programs that we have implemented. And the two bars refer to the baseline scheme and to our construction. So baseline scheme is something that I described much earlier, and hop is baseline with the two optimizations. And the high-level result is that, corresponding to the baseline scheme, we perform up to 240x better. And just so that we can see the y-axis and slow down to insecure execution of hop clearly, let me move this to a logarithmic scale. So the y-axis is now logarithmic. And the high-level result over here is that compared to insecure execution, we perform in the range of 8x to 76x worse. So programs such as binary search, which exhibit no degree of locality, they perform up to 76x worse. But for programs such as Burrows-Willis transform, which have a high degree of locality, they perform up to 8x worse. With that, I have discussed a secure obfuscation scheme, which has been designed with architectural constraints in mind. One key addition that is necessary in this space is some programming language support, so that the developer can easily specify how to use a scratchpad, or hopefully it's not going to be the developer's concern on how the scratchpad is used. So with that, I have spoken about my work on computing on private data and obfuscation of programs. Let me try to speak about my research a little more in general. My research has focused broadly in two areas. One is on privacy-preserving computation, and second has been towards blockchains. In privacy-preserving computation, I spoke about parallelism in oblivious execution and obfuscated program execution. In the first section, I have worked towards a bunch of papers on Oblivious RAMs and Oblivious programs. For example, I have worked towards designing an Oblivious RAM scheme, which actually achieves the Goldrake-Ostrowski lower bound, although we actually change one of the assumptions. That is, we assume a private information retrieval protocol. But for the changed assumption, we show a new lower bound saying you cannot do anything better even in this scenario. I have also worked towards the notion of having an oblivious data structure. So let us say an adversary already knows that you just have a map data structure or a tree data structure, and in that case trying to hide which operations are being performed. And turns out these oblivious data structures can be faster than an ORAM. And finally, I'm presently working towards the notion of achieving locality in conjunction with obliviousness, as well as the notion of achieving perfect security with obliviousness. In the area of blockchains, I have worked towards adversarial behavior in blockchains, where we have tried to attack the Bitcoin protocol, as well as have worked towards the design of robust blockchains, both in the permissioned as well as permissionless settings. With that, let me move on to speaking a little bit about my future work. The overarching goal over here is to move from privacy-preserving computation to a privacy-preserving system. Until now, we have been discussing having private inputs, performing some computation on top of it, and learning some data models. For instance, we considered Netflix ratings as being our private inputs, and user recommendations as being the output. But in an actual system, you may end up revealing this information through other means, through other auxiliary means. For example, if it's the Netflix's example, just the fact that you're streaming movies from Netflix already tells it that I'm watching this movie. And that, in practice, can hurt you. Second, the data model itself, in some cases, can reveal a lot of information about your private inputs. And if that happens, the entire privacy-preserving computation you're doing in between is rendered useless. So you may want to use notions of differential privacy in conjunction with secure computation to ensure that you still have some realistic guarantees on your private inputs. Second, we would want to move on to a broader class of functions, such as doing privacy-preserving neural networks or privacy-preserving genomic tasks, as also design functions that are better suited for secure computation or that are faster in secure computation. Looking at slightly long term, we would want to consider alternative security definitions. One such example over here would be for obliviousness. Right now, we are thinking of trying to hide all access patterns. But what if we were to think of obliviousness as being a spectrum between leaking all access patterns and hiding all access patterns? And now we can try to pick a point in between in a way that you leak some accesses in such a way that you achieve some security for some in some realistic notion. The eventual goal over here is to ensure that a user or an organization can specify policy on how her data or program can be used. And if all such users have such a policy, a company who's trying to provide user-specific features actually adheres to this policy. And the privacy-preserving system actually ensures this. In the space of robust blockchains, I'm interested in combining the merits of the classical consensus protocols and the new permissionless protocols, as well as trying to achieve the notion of confidentiality and efficiency together in blockchains. Before ending my talk, I would like to thank all of my collaborators, without whom none of my research would have been possible. Thank you, and I'd be happy to take questions.
I have one question. You said that in the Netflix experiment, it took minutes, right? Several minutes. Mm-hmm. What if for the unsecure scheme, how long would it take? Seconds?
If we implement this now, the ratio of, for that particular example, the ratio of insecure to secure or secure to insecure is 10 to the 4 with secure computation. 10 to the 4 with secure computation.
10 to the
10 to the 4. So what takes 1 minute will take 10,000 minutes. And if you assume a trusted processor, there has been parallel work at Berkeley. And over there, with the same algorithms, it is around a factor of, I think, 40 to 80.
So why do you think a notion of like non-binary security, like somewhere in the middle, is a good idea?
Because you'll get some notion of efficiency. You're talking about the obliviousness spectrum, right?
Right.
Yeah, so if you can try to reduce the number of accesses or the number of oblivious accesses, you'll get some notion of efficiency.
Right, but like, wouldn't it be very hard to define what security or privacy really means in that case?
That is something that I'm presently working on and trying to understand what security exactly means in that context. You're right, it's not so easy to define. So one notion that can be interesting is the notion of trace differentially private computation, so that you reveal some accesses in such a way that the differential privacy of users is still maintained. And that may not be applicable for all inputs. So instead of thinking of obliviousness as being the worst case scenario, where for any input I'm going to give you a solution, if you have, let's say, maybe a distribution on inputs or something along those lines, you're trying to hide something specific. Again, I'm not being very specific here because this is not something that I have thought about entirely, but this notion seems like a reasonable one that we can try to work on.
One thing I didn't understand is that for the proof of obfuscation, why do they require Oblivious RAM? Because if the program was encrypted, even though the access, it's really hard to reverse engineer the original program, right?
So I think a simple example would be if I have a program which performs binary search versus a program that is adding elements in an array, just based on access patterns, you would not know exactly this is what it is doing, but perhaps you should be able to figure out at some point in time that is what it is doing.
But that only applies to a very simple program, right? If I'm running...
Sure, I think what we're trying to get is provable guarantees in terms of with having a cryptographic proof. So you're right, even in the generic case, it may be very hard to actually construct an attack. But over here, what we are trying to show is that if you have something like this, you will never be able to reconstruct or come up with an attack.
Right. I mean, there are real world cases that people care about the program obfuscation, right? And in those real world cases, is Oblivious RAM unnecessary?
So I would say if in real world cases, if they care about these settings, then you would want to actually hide the program, and in that case, yes, Oblivious RAM would be necessary.
Okay.
So if you're doing, never mind, sorry.
We'll take it offline.
Sure.
Yeah.
Did you have a question?
Oh, that's synthetic.